Okay, let's talk a bit about 2D motion. To start, we're going to look at this and kind of just look at representation of motion in terms of vectors, because that's the tool we're going to use for this. Now we're going to look at two particular examples of motion in 2 dimensions, those being projectile motion. So, you fire a nice projectile like a cannonball or a spitball or any kind of ball, basically. It goes in this nice little like whoosh parabolic arc that I just gestured with my pen. You can imagine it, but you can't see it because I'm not filming it. And right. And then the other example we're going to look at is uniform circular motion, which is motion that happens when you go uniformly around a circle, hence its name. It's actually it's a good example. It'll come up a couple times in a couple of contexts, and so it'll be useful here. To start, let's consider a ball. And this ball, I'm going to fire. Whoops. First of all, make sure I have the right colored pen up. I'm going to fire it to the right in the real world. And what I'm going to do is I'm going to think of this real ball, this one here, as being built up of two pieces. One is a ball that is just being dropped vertically, and one is a ball that is just moving horizontally. I'm going to isolate out the vertical and the horizontal motions. In the vertical case, we know that the initial velocity is 0. We know that the acceleration is g, if it's on Earth, basically. And that's about all that we know. In the horizontal case, neglecting air resistance, we know that the initial velocity is some initial speed, and we know the acceleration is 0, again neglecting air resistance. This we've done before. We've done things falling, we've done things going out. What we haven't done is combined them. And to combine them, we now need to note this is talking about the information in the y direction. This is talking about the information in the x direction. And we need to be able to put this together. This is where vectors start to come in. So we would now say things like the initial velocity, the vector, looks like v naught I hat plus 0 meters per second j hat. Or what is slightly more common in my preference, I tend to write it more like this. They call bracket notation, where this is the x component of my vector. This is the y component. So similarly, the acceleration would then be 0 meter per second squared I hat plus g j hat. Or, in bracket notation, 0 meters per second squared, comma, g. You will occasionally see also, this is unit vector notation, I should say. You will sometimes see, instead of I hat, j hat, and then k hat, you will see x hat, y hat, and then z hat. So, but if you're doing this, unit vector notation, this is bracket notation. All that we're doing is condensing this information that we've got. We're saying we have vertical information and we have horizontal information, and using vectors helps us to just keep things organized, if that makes sense. Now, let's take a look at an example where it's going to help us. We have here a slingshot, which is launching a pellet with some velocity v. And we can see this velocity v is directed at some angle theta above the horizontal. So, I have v, the vector. I can look at this and I can say, well, all right, if I were to really kind of dig into this thing, v, the vector, has some speed v, in this direction theta. And so I can split it up. That's what this little symbol is doing, is it's indicating I'm breaking this into components, to an x component and a y component, vx and vy. So v equals vx in the x direction, vy in the y direction. Being an excellent student of trig, I happen to furthermore know that vx, oops, hold on, bracket, is the speed v times the cosine of theta, and vy is the speed v times the sine of theta. So that's nice. What this lets me do, though, is to start working these problems. I can now take one whole problem, and I can use all the x information. I can do another whole problem using all the y info. And generally speaking, whatever happens in x doesn't affect what happens in y. Whatever happens in y doesn't affect what happens in x, except for one thing. They both share time. And not like in a timeshare sort of thing. That'd be weird. But that the time of flight in the x direction and the time of flight in the y direction is the same time. It's flying. You know, when it stops flying in x, it's also stopped flying in y. So a common setup might be to look at this and say, all right, I know, let's say, I know that the acceleration in x is 0 meters per second squared. I know that the initial velocity in x is this v cos theta. I want to know what delta x is, and that's all I've got. And in y, I know that ay is equal to, I guess now minus g, because I made this y positive. If that y is positive and it's going up, then acceleration is negative because it's going down. I know that the initial y velocity is v sine theta. And now I could be very clever, and let's say I want to know what happens for this thing to return to its initial height. So maybe there is, you know, set up somewhere way over here, a basket that is at the height of the slingshot, more or less. So that, you know, if I were to go, that's not really accurate. So maybe the basket is up here. It's just kind of supported. So this is at the same height as the slingshot was, right? That totally looks believable. Yeah, I could believe that. All right, sure. Anyway, point is, that would tell me that delta y would be 0 meters, because its initial height and its final height are the same height, so final minus initial is 0. This I could then use to solve for t. And once I've done that, I can use that same time over in my x setup. This is the basic premise of basically every projectile motion problem. You have enough information to solve either x or y, and then you need to take that information you get and bring it back over to the other dimension. Right. The last thing I want to talk about is uniform circular motion. And so in uniform circular motion, we have an object here chilling out on a trajectory that is circular. This is totally circular. You may need to adjust your monitor, but it is circular. It's a circle of radius r, let's say, to be convenient. And it's traveling. So what does it mean that it's traveling? That means that theta is changing with time. Right? So, what does that mean? Well, let's take a look at one thing that happens when we deal with vectors. I want to know what the velocity is. Well, the velocity is the rate of change of my position. Yes? So to do this, I'm going to differentiate this whole thing over here. r sine theta, or, wow, I'm struggling with my, sorry, not awake apparently, r cos theta, r sine theta. The way that we take the derivative of a vector is that it's going to distribute, much like you would distribute something that's multiplicative, although it's a derivative and only kind of looks like multiplication. So I'm going to take the velocity, or sorry, take the derivative, seriously struggling with words. The derivative of the x component will be the x velocity, and the derivative of the y component will be the y velocity. If I look at this, r, this being a circle, r is constant, so I'm just taking the derivative of cos theta, which would get me then, by the chain rule, r d theta dt times sine theta, and then r d theta dt times cosine theta. So if I were to pull this out, I see I have r d theta dt sine theta cosine theta minus signs are tricky. So this, I'll leave this as an exercise to the viewer. This is my speed, this r d theta dt. And this minus sine theta cos theta. This is the direction of my velocity. It is a unit vector in that direction. And so what direction is this? What is minus sine theta cos theta? All right? So the x component of my velocity is now the opposite of the y component of my position. So I've taken this, which is positive, and now I'm going to make it negative. And then the y component of my velocity is the x component of my position. So this is going up. So I have, minus my y in x and plus my x in y gives me my velocity. What you see here, and what should not be terribly surprising, is that the velocity is tangent to the curve here. This, keep in mind, is technically a trajectory. So we expect derivatives to be tangent to curves when we take the derivative with respect to that variable. So if I have a position versus time curve, we expect the velocity to be tangent to that curve. It's nifty that it happens to also be tangent to the trajectory, but that's not as intuitive or obvious as you might think. Anyway, if we were to continue on once more, and I wanted to say that the acceleration is the derivative of the velocity, well, that means taking a derivative of this whole thing. Right? Now you might get worried that I'm going to have chain rule shenanigans, but we said this was uniform circular motion, so v is a constant. So all I'm doing is hitting my unit vector here, this minus sine theta cos theta with a derivative. And that's going to pull out just like before. I'm going to get minus d theta dt from the chain rule cos theta, then minus d theta dt sine theta, again from the chain rule. And so we have here minus v d theta dt cosine sine. Writing is hard. If you need to pause and do the math step by step, please by all means do. Or just believe me and see where you can go with this. This is thus my acceleration. because this is a brand new unit vector over here. And so if I instead put this inside, something kind of interesting begins to happen, which is sort of a novel thing to see, and we'll talk about it more. The reason I do this, vectors have a magnitude, which is always positive, and a direction, which is where the minus sign belongs. This direction, though, if you go way back up to the beginning, should look kind of familiar. This was our original position vector, right? And I can write this as its magnitude r times cos theta sine theta. That looks familiar. This is pointed in the opposite direction of the position vector. The position vector points from the center outward radially. This points from our point inward radially. Kind of nifty. That's where the whole idea of centripetal motion comes from. Anyway, we will come back to this when we get to forces as well. So uniform circular motion is a good example of kind of the benefit of the power of vector notation in terms of analyzing a situation. You're not going to be called upon too often to employ this, but it's nice to kind of see how it organizes and can make life neater for you and pull out some geometric information. In terms of projectile motion, this setup where you're dealing with problems in terms of x and y, that's key. That is kind of the major problem-solving technique that's getting into play here. There are some new things to identify, just like starting from rest or dropped helped you clue in on information in one-dimensional motion. There are similar clues that will come in here. Tricks like pinning down what its delta y is, or figuring out what you know about x or what you know about y, which one you can start with, are the basic tools. And then all this is made possible thanks to the wonders of vectors. Whether you do unit vector, bracket, or find some other means that's of interest to you, I don't know another one off the top of my head, this is a relatively concise way to carry this information about multiple dimensions. Other than that, 2D motion is a lot like 1D motion. If it's with constant acceleration, so if it's free fall problems of any sort, you can bust out those constant acceleration equations. If it's not constant acceleration, then you're going to have to resort to calculus and carry out some derivatives and integrals, and those, like we were showing down at the end, are carried out term by term, basically. You carry that out for the x term, you carry it out for the y term, and they don't cross over. Right, have fun.